So um, let's look at a polynomial x to the fourth minus 100x squared plus 2000x plus 5000. Okay? So if we want to look at the end behavior, what happens as the numbers, the x values get huge or they get super small in the negative direction? Let's start at 0. We have 4 terms. When x equals 0, which is the most powerful of all 4 of those terms? The 5000. Everybody agree? When x is 0, this has more influence on the graph than anything else. Okay? When x equals 1, which one is the most powerful? Still the 5000. When x equals 3, which one is the most powerful? The 2000x. When x equals 3, how much influence does x to the fourth have on the, well, when x equals 0, how much influence does this have? None. No influence at all. Okay? When x equals 1, how much influence does that have? Not much. Right? What about when x equals 5? Well, this would be 25. Well, let's go back to, we did 3, right? So 3, this one would be the most. And 4, 25, 16 times 100 is still not bigger. But can you see that as x gets bigger, this one stops being important? Right? And as x gets bigger, this one stops being important. It still affects the graph a little bit, but as x gets bigger, this becomes less important. And eventually, x is so large, the only thing that matters is the x to the fourth. Do you see what I mean? If we plugged in 25 million, this would only be 25 million times 2,000, which is a big number, but it's not nearly as big as 25 million to the fourth. So the height of the graph at 25 million is influenced more by x to the fourth than any other part. In fact, if x was big enough, we could go ahead and erase all of those, and the graph would be so close, x to the fourth would be so close to this other graph that we wouldn't be able to tell the difference. Does that make sense? Yeah? Okay. Same on the negative side. As x gets closer and closer to negative infinity, the rest of the graph loses importance. So if we wanted to look at end behavior, all we really need to look at is the first, the leading coefficient and the degree of that coefficient. Does that make sense? Which we've done before, right? We've done a little bit about that. Okay, so these rational expressions have vertical asymptotes that we learned about yesterday, and they also have holes, but they all have horizontal asymptotes, which affect the end behavior. For instance, you might have one that looks like this. So that gets closer there, that gets closer there. So as x goes out to infinity, what does y approach? It approaches, well, 2, right? So as x approaches negative infinity, y also approaches 2. So our job today is exactly what we did yesterday, but we also want to figure out where the horizontal asymptotes are, which describes the end behavior. Where do the ends of the graph get closer and closer to? Sometimes they get closer and closer to 0. Sometimes they get closer and closer to a number that's not 0. And at other times, they get closer and closer to a slanted line like this. And we need to figure out, is it 0, is it some other number, or is it slanted? A what? Oh, no, it's super easy. No, it's not bad. Okay, so, well, let's consider a couple of rational expressions. And the one that you need to know first is 1 over x. 1 over x looks like this. Okay? It gets closer and closer to 0. Because when does this equal 0? It can't. How come? Right, it would be infinity. If you want to get a 0 out of a 1 divided by something, I mean, 1 divided by 2 is 0.5, 1 divided by 3 is 0.3, 1 divided by 4 is 0.25. Those numbers are going to get closer to 0, but will they ever reach 0? Until you get to calculus, and 1 divided by infinity is 0. But we're not there yet, so we can't. So if I had a over b, and I knew that it equaled 0, what can you tell me about a and b? A has to be 0, and b is not allowed to be 0, right? The only way for a fraction to equal 0 is if the top equals 0. And the bottom is not allowed to be 0. What is 0 over 0? Well, we don't know. Well, sometimes it's infinity, sometimes it's 1 or 7 or 8 or any other number, and sometimes it's 0. It just depends on how big your 0 is. Some zeros are bigger than others. Well, it's just like what is infinity divided by infinity? We don't know. It could be infinity, it could be negative infinity, it could be 0, it could be 1. It just depends on how big your infinity is. So how can you have a 0 that's bigger than another 0? And the answer is, if you have two functions that are getting closer to 0, if one gets closer a lot faster than the other, that's where you run into trouble. Yeah. So, you know those sequences we did last year? And that's, again, that's all calculus stuff. Sometimes 0 over 0 is 1. Sometimes it's not. It depends. Okay, so 1 over x can never be 0. What about 1 over x squared? It can never be 0. In fact, 1 over x squared looks like this. I've got an issue. 1 over x squared looks like that, and then 1 over x to the third is a lot closer, but it looks like this. And 1 over x to the fourth would be really, really close. And then you go on. So the even multiplicities go in the same direction, and the odd multiplicities go in opposite directions. It would flip this way. Yeah. Well, it would go from here to here. Right. Okay, so anytime we have 1 over x or 1 over x squared or x to the third or whatever, the graph will never equal 0. So let's take two polynomials, 3x squared plus 6x plus 4, and 4x to the third minus 6x plus 1. At the ends of the graph, the only things that really matter are the first numbers. Because eventually, this 3x squared is going to be so big that none of this stuff matters. Right? Now, the size of these will tell us how fast we get close to the ends. If these numbers are really big, which they're not, then it will take longer to get there. But if those numbers are really small, we get there a lot quicker. So we can erase this. So essentially, that rational expression on the ends can be simplified to 3x squared over 4x to the third, which is really just 3 over 4x. When does 3 over 4x equal 0? Never. So in this case, this has what is called a horizontal asymptote at x, oh, it's a y value, sorry, at y equals 0. You see what I mean? So what I did is I took the original rational expression and I threw away everything but the first numbers. And I get 3x squared divided by 4x to the third, which simplifies to be 3 over 4x, which is a graph that is almost identical to 1 over x. And this graph equals y. There is no way it can equal 0 because the top number is a 3. So this graph here is really similar to this graph on the ends. In the middle, they're different, but on the ends, they're so close we can't tell the difference. And this graph on the ends is so close to this graph on the ends that we can't tell the difference. And this graph on the ends can never equal 0 because there's an x in the denominator and not in the top. Okay? All right, so let's look at another one. So what if I had 8x to the third, and I don't care what else is there, and I divided it by 2x to the third. Okay? The whole function is really close to this function, which is really close to y equals 4. Because 8x to the third divided by 2x to the third is 4. So that graph has a horizontal asymptote at 4. There is no way that this graph can equal 4. It's impossible. Does that make sense? So when I draw this graph up here at 4, and I don't know what it's going to look like, something like that, but it will never equal 4. Because when we simplify this down, the x's cancel and 8 over 2 becomes 4. That is the number it will never reach. Okay? What about this? Oh, wait. I did that backwards. Sorry. Okay. Now, the entire function is really close to this. And if I simplify that down, I get x over 2. Okay, this is where it gets a little confusing. Katie, you paying attention or are you playing with your hair? Thanks. So, this graph looks really close to the graph of x over 2, near the ends. In the middle, it doesn't look anything like it. But what does x over 2 look like? Oh, come on. It's a line with a slope of 1/2. It's up 1 over 2, right? So this graph, this graph does not have a horizontal asymptote. This is called a slanted asymptote. So if I graph the line 1/2 x, then it would look something like this. And it's slanted. Now, you're not going to see this in this class, but what if I had 6x over 6x to the fourth over 2x squared? Then my slanted asymptote is actually 3x squared. So I would graph 3x squared, and it would look, it depends, but it would look something like this. Well, it can go, remember, in the middle, that's not true. This is only true close to infinity and negative infinity. So you can go through the asymptote as many times as you want, as long as it's not way out there. And it might it might have an asymptote in there. But we will never see a quadratic asymptote. They just don't do it very often. Okay, but it can happen. Well, we're still trying to understand polynomials so that when you get to calculus, you'll know what you're doing. Yes. Okay, so the other part today, which is so much easier than what I just taught you, is where do these graphs cross the x-axis? And that's super easy. We learned about it before. So if I have some function, some polynomial divided by some polynomial, which we'll put in the form a over b equals 0, we came up with two rules. A had to be 0, and b is not allowed to be 0. So if I had x plus 2 times x minus 1 over x minus 1 and x plus 3. Let's go through all of the rules. Okay, so my graph is going to look like x plus 2 over x plus 3. But it has a hole at 1 and a vertical asymptote at -3. Does it have a horizontal asymptote? Well, this would be x squared divided by x squared, which would be 1. The HA is at 1. X is not allowed to be 1 or -3. This is a hole, and this is a vertical asymptote. Does that make sense? No, it's not. Well, hold on. Don't get confused there. So what I want to point out here is the only thing we're going to add to this are the x-intercepts of the graph. Where does this graph cross the x-axis? Well, we have a fraction that equals 0. So we need to find the numbers that make the top 0 that don't also make the bottom 0. So we set these equal to 0. And my x-intercepts are -2 and 1. But 1 is in the not equal to list. So if Santa comes and your name is on the good list and the bad list, you're on the bad list. So you will kill Kris Kringle. So can we have an x-intercept on the same place that we have a hole? No, because if you get close to the x-axis and then there's a hole and you go through it, there is no x-intercept. So you set the top equal to 0, but if that number creates a hole, it can't also create an x-intercept. Okay? So we need to remember 3 things about horizontal asymptotes. If there are more x's in the bottom than in the top, the y value can never be 0. If the x's in the top match the x's in the bottom, you divide them, and whatever number you get is your horizontal asymptote. If there's one more x in the top than in the bottom, you divide them, and the equation you get left over tells you the slanted asymptote. So if we end up with 1 over x, then your HA is y cannot be 0. If you end up with, like, well, let's say 2x squared over x squared, then your HA is y is not allowed to be 2. Because your x's cancel and you're left with 2. So if we have 4x to the third over 2x squared, that equals 2x. So that means the graph never touches the line 2x. Well, near the ends. It could touch it in the middle, but near the ends it never touches 2x. So all you really have to remember is if everything cancels, that number is your HA. If it simplifies down to something like 1 over x or 5 over x or 1 over 2x, that graph never equals 0. And this is just a line that the graph is not allowed to, a slanted line that the graph is never allowed to touch. At the ends, right. In the middle, yeah, you can. Because that trick where we threw away all the other numbers only works when the x values are huge. Right? In the middle, the graph can wiggle all around, and it might be equal to 2x. An asymptote is the graph that a line approaches, and it near the ends. We never say that, but near the ends. You can go through the middle of the asymptote lots of times. So I knew today was going to be hard. I'm sorry. Okay. But I didn't say it was going to be hard because Amy's head would have blown up. And she was happy with me before she came in. Okay. Maybe, one time my friend asked me, is it the whole world that has the problem or is it me? No, I'm not going to answer that. All right, look at number 1. So I'm going to pull out a 3, x squared plus x minus 6. So this becomes 1 over 3 times, that's that factor, x plus 3 and x minus 2. Okay? So now we've got to go through and list everything we've talked about before. We're not going to graph this one. We're just going to list it. So what is x not allowed to be? -3 and 2. Everybody follow so far? Hey, -3 is what structure on the graph? What type of asymptote? It's a vertical asymptote. It didn't cancel. So 2 is what type of structure? It's also a vertical asymptote because it didn't cancel. Okay? Now, we need to figure out the x-intercepts. What x value makes the top equal 0? There are no x's up there, right? So this has no x-intercepts. It never crosses the x-axis. Does that make sense? Okay, and now we need to look at HA. So we look at the first number on the top and the bottom, 1 over 3x squared. No, x or y cannot be 0. So if the bottom is bigger than the top, your horizontal asymptote is at y equals 0. So my HA is y equals 0. There is no way that graph can hit y equals 0. Well, so if you leave that off, a true statement is y can never be 0. The equation of the line of the horizontal asymptote is y equals 0. Does that make sense? So the graph never touches y equals 0, right? The dotted line, except maybe in the middle, the dotted line is this equation. So it just depends. Are you describing what it's not, or are you describing what it is? And I'm not going to be too picky on that. Okay? So if you list this, that's true. If you list this, that is also true. The equation of the horizontal asymptote is 0. Okay. Look at number 3. So I'm just going to hurry and factor number 3 to save us some time. X times x minus 3 times x plus 2. And then what would I pull out on the bottom? -3. You always want to pull out a negative if the leading coefficient is negative. So it's going to be -3 times x plus 3 times x minus 2. So now we got to go through and list everything, all of the parts of this graph. No, right. The x's and the 3's will be negative. So no, it doesn't work that way. So, where are the discontinuities? Where does the graph not exist? At -3 and at 2. Are those holes or vertical asymptotes? They're both vertical asymptotes because they don't cancel. So this is a VA and this is a VA. Where does the graph hit the x-axis? At 3 and -2 and 0. Right? Those are the roots of the numerator. So the top, if x is 0, then this becomes 0. If x is 3, then it becomes 0. If x is -2, then it becomes 0. Got that? Okay. What about my HA? I divide these, and what do I get? X over -3. Is that a horizontal line? It's a slant. So it's not an HA. It's an SA at x over -3. I divided the first two terms, and I ended up with the equation of a line. If you divide the first two terms and you get a number, that's your HA. If you divide the first two terms and you get no x's in top and x's in the bottom, then your HA is at 0. If you get the equation of a line, then it's a slanted asymptote. Yeah, so let's actually do number 4. It's a little bit harder. So 4 is x plus 3, x minus 2, and then -4. Oh, I wish these would cancel, but they don't. So that's 3 and 4, so plus, oh, this one does. X plus 3 and x, wait a minute. 1, 4, 3, 1. Okay, like that. Yeah. Okay. So now, where are my discontinuities? Do you know what discontinuity means? Where is the graph discontinuous? Where does it stop being a continuous line? So it is discontinuous at -1 and at -3. Now we have to decide, are those VAs or holes? -3 is a hole because it canceled, and -1 is a VA. Everybody okay? Now we need to find the x-intercepts. So x-intercepts, how do I find those? I set the top equal to 0. So equals 0 equals 0. So my x-intercepts are -3 and 2, but it can't be -3 because -3 is a hole. So if you're on Santa's good list and your bad list, you're just on his bad list. Then, so 2 is the only x-intercept. Now, what about HA? So we divide the first two terms, and I get y equals 1 over -4, which is a horizontal line. Okay? No, if it was x over -4, it would be an SA. In order for it to be a slanted, the top has to be bigger than the bottom in degree. The degree of the top's got to be bigger than the degree of the bottom. Okay, 2 is easy. It's got a VA at 4. It has a x-intercept at 2. It has an HA at 1. And it doesn't have any holes. So let's actually graph one. 5, well, 5. if you look at 5, it's negative 4 over x times x minus 3. That's actually really easy. Nothing simplifies, so that's the graph, right? Which I prefer to graph this version, then you need fewer parentheses. You would need to put a double set of parentheses on the bottom. Well, this one is going to have a VA at 0 and at 3. Has an HA where? They all have HAs. 4 over x squared, it's at 0 because the bottom is bigger than the top. Okay? So let's do number 8 together. Okay, number 8. I'm going to pull out an x. X times x squared minus 9. Oh, I've seen this before. X times x plus 3 times x minus 3. I'm going to pull a 3 out of the bottom. 3x squared minus 2x minus 3, which is 3 times x minus 3 times x plus 1. Everybody follow? Where you lost, Danny? All I did was factored it. I just did it really fast. Super like. Okay, so discontinuities. What is x not allowed to be? 3, 3 and negative 1. What is negative 3? Well, negative 3 cancels, so there's a hole at negative 3. Negative 1 does not cancel, so it's a VA. So on my graph, at negative 1, I am going to draw my vertical asymptote. And then I'll just need to remember that when I draw the graph, there's a hole at 3. Okay, x-intercepts. I set the top equal to 0. What are the roots of this rational expression? 0, 3, and negative 3. But 3 doesn't count because it's also a hole. So 0 and negative 3. So on my graph, I'm going to hit at 0 and at negative 3. And there's a hole at 3, but I don't know where yet. I don't know where the graph is to circle it. Well, can you have a hole and an x-intercept at the same? Oh, I see what you're saying. Okay. So you know that it's going to look like that. Well, that might not be true. Well, because remember, 0 over 0 isn't always 0. I... Wait till you get to calculus and it all makes sense. Okay. What about my HA? Right, I have x to the third over 3x squared, which simplifies to be x over 3, which is not an HA. It's a slanted asymptote at 1/3 x. So if I go up 1 and over 3, that is my slanted asymptote. Now, all I have to do is graph it, but it's a lot easier to graph this version. X squared plus 3x and 3x plus 3. You could graph the original because it's y equals 1/3 x, so it has a y-intercept of 0 and a slope of 1/3. All right, so to graph this, x squared plus 3x divided by 3x plus 3. Yeah, see that x-intercept is not actually a hole at the intercept, because sometimes 0 over 0 is not 0. Yeah, but you can see the slant asymptote. So to graph, I'm going to go up through that number, and up here. Oh, look at this. It actually goes through the asymptote and then comes back toward it. Anybody else want to complain? You'll survive. Do you have answers on the back? Okay, I'll give them to you. Yeah, it's on the internet. Why not?